morning, class. I hope you had a nice weekend. So this is the third video on normal distributions. Before we start, let me mention some things about the course management. We will finish statistics on Thursday. We'll have a review of Bayes' theorem. And then we'll be ready for test 2. It will be an open book test. An opportunity for learning. I think of it as a learning opportunity as much as evaluation of your knowledge. You should do your own work. You're trying to get an education, and that's the main point, but also there's the practical point that the final exam will probably be proctored in some way or other. So you don't want to think about cheating here. You need to take this second test seriously. So you need to check your email and Blackboard frequently. At the very minimum, you should check it twice a week when our class would normally have started. That is at 10:50 on Tuesday and Thursday. But I'll be posting regularly on Blackboard and emailing you a lot. So keep in contact with me. And I'd like to hear from you. I've heard from quite a few of you, but it's one thing to know that you have received the first video and were able to view it, but I need to know how things are going, and so if you have questions or comments, email or call me. Remember, you have my cell phone number, and it's in the syllabus, and I also mentioned that on our orientation video. Let me have your questions and comments. And remember, I'm in my office at the regular time from 1 to 2 on Tuesdays and Thursdays. Okay. Normal distributions 3. All right, so the topic is how to approximate a binomial distribution with a normal distribution. Okay, now this is, from a mathematical standpoint, this is the most interesting thing that we will study about normal distributions. This idea of the relationship between these two is really why normal distributions were invented to begin with, and they were invented by Abraham de Moivre in the early 18th century. There's Abraham there. So you remember binomial distributions are discrete. In other words, I know you can't read my writing here, but I'll try to make the point visually rather than by writing. So when we look at a binomial probability distribution, we have these vertical lines, and there are gaps between the lines. distribution is, its density function is a continuous curve. There are no gaps. So, if we want to find the probability that the random variable falls in a certain range, we add, suppose we want to know the probability that the random variable falls from here to here. We add up the lengths of these three lines, but when we're using normal distributions, we look at areas, you remember. So we add the three lengths together, here we find area. Let's have an example to show how the relationship between these two things works. Okay, so the example is, let's toss 100 coins. X is the number of heads we get. And let's calculate the probability that we give, let's calculate the probability that X falls in the range from 55 to 58. And we're going to do it two different ways. So first, the exact calculation. Working with the binomial distribution. Okay, so we have a formula. What we do is we add up 4 probability values. So you remember our formula, I hope. 55 heads, 45 tails. That's 100 choose 55 over 2 to the 100th power. That turns out to be 0.04847, about a 5% chance. This one is 0.03895. This one is 0.030068. And here we get 0.022292. And we add them together to give us this probability. Turns out to be 0.13978. Okay, so that's our first answer. Let's write it here. Okay, so there's about a 14% chance that we get number of heads is in this range inclusive, so 55 through 58 inclusive. Now, let's rework it using the normal distribution. And this is a very significant idea in the history of probability theory. So how does this go? Okay, now we need to know the mean and standard deviation of this random variable. So if you toss 100 coins, the mean is 50. You expect about 50 heads and 50 tails. The variance, you remember, is n over 4, which is 25. So the standard deviation is the square root of 25. So we'll recalculate using normal distribution y with mean 50 and standard deviation of square root of 100 over 4, square root of 25, which is 5. So these parameters here have the same values as the binomial distribution. Okay, now here's what happens. Okay, so we have these 4 vertical lines whose lengths we just added up for 55, 56, 57, and 58. What we do is it turns out that the normal distribution closely but not exactly fits the binomial distribution. So here comes the normal distribution. We have this normal curve here. Okay, so the x is the green vertical lines and y is the black curve. Now, the trick is this: we go a half unit beyond the 2 limits, so we go from 54 and a half to 58 and a half. We extend the interval a little bit. And we calculate this here. Okay. The idea, let me write it for you. The probability that x is between 55 and 58 is approximately the probability that y, subtract a half here and add a half here, is between 54 and a half and 58 and a half. Okay, now I'm going to have to erase a little bit now, but we saved our previous answer so we can do a comparison. Okay, now this is a routine calculation. We learned how to do it in the previous videos. Okay, so this is 2 continued. So this probability is approximately the same as this probability. All right, so this is binomial, this is normal. All right, now what do we do here? Well, we find the z-values for these 2 numbers. That number, this number. Okay, so what are they? 54 and a half minus 50 over 5 is 0.9, I think. Right? 4 and a half over 5. $58 and a half minus 50 over 5 is 1.7. And step 2 is we use the area table. Okay, so continuing, the probability that y is in this range is the same as the probability that z is from here to here. Okay, so we have 2 values of z that have the same sign. You remember how that works. We look up the 2 areas and we subtract rather than add. When the signs are the same, the 2 terms involved in the calculation are different. So if you look those areas up, you get the following. And 4554, that's the area from 0 to 1.7 minus 0.3159. So that is 0.1395. Okay, so that answer is not exact, but it's quite good, 0.1395 as compared to 0.1397. So this answer is accurate to 3 significant figures. The larger value of n, so here n is 100, the better agreement between the 2 answers. This is anything but obvious because the formulas involved seem to be very, very different. I mean, so when we calculate, in the first solution, when we calculated the 4 terms, we were doing binomial coefficients and powers of 2. 100 choose 55 over 2 to 100. This calculation involved that weird curve that we used our graphing calculator to display before we had the pandemic force us to be an online course. Okay, so it's a important achievement in mathematics. It happened in the early 18th century. Now, we can do the exact calculation without much trouble, but it wouldn't have been so easy back then. People were very good at computing then because they, by hand, but they no one would look forward to doing that calculation I showed you earlier. If we had a tail, it would be even more hard to do exactly. So suppose we wanted suppose another problem. Suppose we wanted to find the probability that x is greater than or equal to 55. Okay, now even using your scientific calculator, this would not be a pleasant calculation, because you would have to add up a whole bunch of terms from 55, 56, 57, all the way to 100. So the exact calculation is hard with a scientific calculator, easy with a computer. But it's easy to calculate the probability that y is greater than or equal to 54 and a half. So here we're using a normal distribution. This, of course, is a binomial distribution. As a matter of fact, we essentially have already done it, because we already have the z-value for 54 and a half. So the probability that we get 55 or more heads is almost the same as this probability. And then our z-value was 0.9, you remember. Okay, so how does that go? We have a tail with a positive z-value. So we look up the area between 0 and 0.9, subtract from 1/2. So that's a half minus 0.3159. Which would be maybe it's 0.4, let's see, yeah, 0.3159. So that difference is 0.1841. Okay, now you can do these sorts of calculations also for the general case. You remember, this is an unbiased binomial distribution. So in class we had the experiment with the one pair of hands, if you recall. In that sort of context, you can do the same kind of approximation. You just have to remember your formulas for mu and sigma. I'll let you review that for yourself. Okay, so on Thursday we'll review Bayes' theorem, and then next week we'll get your test to you. We'll start our linear algebra. Now we're gaining a class because we don't have to have our class period for testing. We are slowing the course down. We're not covering as much material. I will be giving you a revised agenda, so you'll see where we're headed as we finish out the semester. So thank you very much. How much time, Sean?